Hello, today we're going to talk about the components and process simulate in a crop model. And to start our class, I'd like to bring this yield level and simulate process where we are talking about the types of yield and the yield level. How we discussed last class that crop models are divided in different components, and when you turn on or turn off these components, you can simulate different things and different interaction inside of the crop model. And to understand this, the models are building based in this type of field and based on the process that I want to simulate. The first level that you have is the potential yield, where determining factors are including, for example, solar radiation, temperature, CO2, and genotype are the main factors that define the potential yield for a crop. So see that we don't have problems with water, with pest, with disease. So you have this potential yield, the maximum, wonder that solar radiation, that temperature, CO2, and genotype that define this potential yield. In this level, generally the model simulates these processes: phenology, leaf area, biomass production, and the partitioning and yield. These are the main process that the model simulates to get the potential yield. So sometimes we need to measure these parameters for this potential condition to understand how our crop are being affected by these different conditions. The next level is attainable yield limited by water, where the determining factors are including plus the limiting factor. In this case, we are looking just for water depth or surplus, when we have more water than the soil can store. So applying this factor, we reduce the potential yield to another level, limiting the yield by water depth, right? And in this step, the main process that we are simulate are the water balance and the crop response to water depth or surplus. And in this condition, we can include here irrigation to change the simulation. So you can see that we have this factor determining the potential yield associated with the limiting factor, in this case water in the soil. We have the attainable yield, and in this step we simulated the water balance and the crop response to this condition. And we have here a next level that is attainable yield, but I include water plus nutrients to penalize the attainable yield or potential yield to get this attainable yield for this specific condition. We also have determined the limiting factor affecting the yield, and we include here the effect of the nutrient for the crop. And in this process, we simulate, in additional to water balance, we also simulate nutrient balance in the soil and in the crop, and how the crop will respond to this nutrient balance. So see that you have this different level with different process being simulated. I start with phenology, Lithara, biomass production and partitioning and yield. After, I can penalize this growth by water balance and the crop evapotranspiration, the limitation of this crop evapotranspiration that you limited the photosynthesis. And in the end, I can include the effect of nutrient balance. For example, the most model make this the effect of nitrogen on the crop growth and development. So we have these different processes occurring in the model, and each one is interact with others to make the crop grow more realistic. And we can have here our last yield level, that is actual yield, where I have determining, limiting, and reducing factor, penalizing the potential yield to get this actual yield. In the most case, this is the value that I get at the plot in the farm. And here we have the factor that they are reducing this attainable yield. I can include here pest and diseases. These are something that the models are start to being developed to interact all these factor with another limiting condition that will reduce the yield. So here we can make this simulation and include in the system to interact with the other factors. For example, there is a model that simulates disease development, and this type of disease affects Lithara Index here in this process. So I have a potential condition that is when I don't have disease in the plant, but when I have disease, I penalize the leaf growth area, and this leaf area will affect the biomass production, will affect the crop transpiration, will affect the nutrient stock in the plant, and this will affect the final yield in the system. So looking for this potential yield, we have these different processes that are simulating the model. This is a representation where this factor can be included. Some models have less process, some models have more process occurring or simulating. Here we'll look for phenology, leaf area by plant, biomass production, and biomass partitioning when you are looking for potential yield. After you're gonna look for the water balance to affect the crop, and we also have in the book some chapter about nitrogen balance in the crop. So to start here, we're going to talk about phenology. We have these four factors mainly that affect the crop phenology. We have temperature, photo period, vernalization, and water depth. Depends on the crop and the environment that I am simulating. We have this four factor occurring. So to start, we need to define what is phenology. Phenology is the study of the progress of the development of stage in the plant cycle and how they are influenced by environment factor. Here we have two examples of a phenology. We have this example for soybean and this other example for coffee. For soybean, we have the emergence, we have the vegetative period until the crop starts the flowering. After the flowering, the crop starts the seed growth until get the maturity, and we have here the harvest. So this is the most useful phenology used for soybean in the world. And here in the right you have example how the coffee flowering growth along the time. We have here no flower. The crop starts to develop the flower until open, start to develop the grain, different colors until the end when I make the harvest. Why this is important for the crop model? We talked in the last class about the driving variables. So a phenology, it's a state variable that defines what condition the crop is in that moment. So the phenology will control different processes in the crop model. For example, the biomass partitioning will follow the phenology. For example, in the vegetative period, the crop puts more biomass to leaf growth, root growth in the beginning of the cycle. But when we change the phenology to flowering, the crop starts to reduce the biomass to leaf and increase the biomass being put in the grains or in the flower. And this will change until here when you have the grain filling period where the crop will put all the biomass production in the grain, and we will start the translocation of nitrogen from leaf to the grain. So this phenology will affect this process, for example. And other process, the radiation use efficiency, also can be defined by the crop stage. For example, Here in the beginning of the cycle, the plant is producing more leaf, more stem, that has a energy cost lower than when the crop is producing grain. So we can use this approach to simulate the biomass production here in the vegetative period. But when I am producing grain that has a higher cost, energy cost, I can put this uh, change this radiation use efficient for this period. Okay. So based on this information, we have this four main environmental condition: temperature, vernalization, photoperiod, and water availability. Today we're going to focus on to understand how temperature can be modeled and how most of the models use temperature to, to be a driving variable for phenology, and how we can make this simulation. Okay. There is a very simple model that is the thermal time. It's a linear approach where the crop development is estimated based in the mean air temperature less the base temperature for this crop. What is this base temperature? It's the minimum temperature that the crop needs to develop or grow. Below this point, the crop no grow because it's too low the temperature for this crop, and the crop can't do all process, photosynthesis and other activities in the plant adequate, so the crop stop the growth. Here we have this very simple model where every day I make this calculation to get how much thermal time the crop accumulates each day, and when the crop reach this total thermal time that the crop needs to complete a phase. So we can estimate in thermal time how many days the crop will spend to reach flowering, for example. So remember that last class we talked about hypothesis. So to me, use this model, very simple, mean air temperature less base temperature. What we define as the model hypothesis. Phenology responds linearly to air temperature. Temperature increase, the crop increase the development. Mean air temperature is not lower than base temperature, so this can't be a negative result, only positive. The mean air temperature is not higher than lower optimum temperature. So when the temperature is too high, the crop starts to reduce development, so the environment can't have a temperature higher than the optimum. So here we have an example of one type of the temperature function response in function of the temperature. So here we have the base temperature. So after below this point the crop can't grow, and a higher value from this point the crop will get an increase of development until reach the maximum at this optimum temperature. This model just can be used if I have an environment temperature from this point until this point, because our model is linear. So if the temperature is 30, for example, our model will calculate a increase of the rate, and the crop doesn't work on this way. This model is the best way to make the development. Maybe if I am in this range or my crop has a higher temperature, optimum temperature, I can use this model because it's very simple, and I'm gonna go simulate what I need to, to get the results for phenology. However, the real crop response follows this function. Okay, I have here a lag phase, a point where this is the optimum temperature, and here is the maximum temperature that this crop can survive, and we can use this approach where we have the no development if the temperature is below this point, increase into the maximum development, and after this optimum temperature, the development starts to reduce because it's too hot for this crop until reach this point where this is the maximum base temperature where the crop can't grow after this point. So this is the real response. What is the problem? It's too hard to get these specific parameters to building this curve. So we have some alternatives to simulate this response, but with less parameters required to make this simulation. So this approach, when you have more than one optimal or base temperature, we call the cardinal temperatures, where the model hypothesis the crop is not sensitive to photoperiod, because at this level we are not including the effect of the photoperiod. Our crop is just responding to temperature. The crop do not have limitation related to water depth, nutrient, pest, disease, and weeds that affect the development of this crop. So to start this model, we need to define each phenological stage need to be simulated. What is important for a model? I need to simulate all these phenological stages, or just vegetative and reproductive period is enough for me. I need to define this. And the other question is, each function to represent thermal time and the parameter will be used. Each one is the best one for my model, for my proposal. So, based on this information, we can start here with functions and parameters. Here is the real response for the crop. We have this curve, and you can make some adjustment using Spline's equations. Here we have one possibility where I have this linear of two segments. I have a linear period where the crop is increasing to the optimum, and after this optimum I consider that the crop has a maximum development by day occurring after this temperature. This is one possibility. Another one is use a linear with 3 points. So I have the base temperature, I have the optimum temperature, one value, and we have the maximum temperature for the crop. So very similar with this response. And we have the third option, that is the linear with 4 points, where I have the one base, two optimum temperature, and the maximum air temperature for this crop. So we can use this approach here to estimate the development of the crop. Okay, so I have these three options, different models using these three approach. For example, the aqua crop use this approach here, the Epstein use this approach, and the SAT use this approach. Each one is the best. I need to look what is my M, what I want to simulate, and how is the environment that I am simulating this condition. Okay, and if I get this 4 points curve here, I have this different value. I have the base temperature, the superior base temperature, and two values of optimum temperature for the crop. So getting this function, I can make some approach here to make this simulation. Here we have the code or description of this curve in the model. For example, the temperature function will be 0 if the environment temperature is below this value here. So if the temperature is below the base temperature, this will be 0. Okay, what this means? If I have one day in the calendar and the temperature was below this point, the crop will not accumulate development. Okay, and here I have the description for this range from this point to this point. If temperature is between one, the optimum one and the optimum two, the value is gonna be 1. Here is the description for this decrease here, and if the temperature value is over the upper base temperature, the value will be 0. So environment temperature is high or similar to TDC, the development of the crop is 0. What does this mean? If I have temperature between this range, the crop is in the maximum development by day. So if I have this value, the crop will accumulate 1 day or the maximum unit of the thermal time for that day. If the value is 0, the accumulator will be 0. And if the value of the temperature is like 10 degrees Celsius, I get this 50% of development. So here I have 0, here I have 50% of the accumulate, the required thermal time by day, and here I have the maximum. So if temperature is in this, I have 100% of the accumulate thermal time in that day, and if temperature is here, I have 50% of the accumulate. So dependent on the temperature, the crop will have high or lower development in this condition. And the next step in the crop development is to define the parameters. So in our equation, we have these 4 parameters. We can make measurement in the experiment to define this point, or use reference to, to get these parameters. So for example, for wheat, we have here the base temperature 0, we have the optimum one 25 and the optimum 2 28, and the saline temperature for development, that is this point, the upper base temperature, we have this value of 40. So this is a good start for make this simulation. It's important to highlight that each model can have different parameters, so the thermal time required to complete a stage can change by each model, so I need to be careful during the calibration process to define this condition. And here is the next step in this simulation. First, I get this temperature function following this approach, and after I calculate the thermal time by day, daily thermal time, where the daily thermal units here, it will be function of the optimum temperature less the base temperature multiplied by this temperature function. For example, if I have here for the wheat that I have 0 and 25, I have here 25 is the maximum of thermal time that the crop can accumulate in that day. If I have the temperature inside of this range, I'm going to have 25 degrees Celsius by day accumulate. But if I have 0, this value is going to be 0. But if I have 0.5 for temperature function, the accumulate will be half, 12.5. Okay, and this value is accumulated by day along the crop cycle, and this total accumulated thermal time will define when the crop will change of phase, for example. So to change the phase, we can accumulate 500 thermal time units or 1000. I need to measure this for the crop and define when this will occur this change. So this calculation needs to be done to define the state variable for phenology that will define other factors inside of the model. And here is a diagram showing how the submodel of phenology was developed, or each factor are affecting. So we have as the driving variable here the temperature, the mean daily temperature, that is the input of the system, I have four parameters: the base temperature, the two optimum temperatures, and the saline temperature that will affect our temperature function. Based on this temperature function, we will find the daily temperature unit that is calculated by day, and the end I'm gonna have the cumulative temperature unit that I know for each phase how much cumulative thermal temperature unit the crop needs to change the state variable across the time in this system. Okay. So in the book, we have more detail about photo period and vernalization effects on phenology. And the next step that you can simulate for potential yield is the leaf area by plant. For leaf area, we have this different approach, and it's important to simulate leaf area because it's a driving variable, but also a state variable, but is a drive variable for interception of solar radiation and biomass production. We have three approaches that are mainly used for this process. We have this carbon-based method, temperature-based method, and combined methods. The carbon-based methods, the dry matter, the carbon that is computed by simulation, produced is partitioned for the organ and with the specific leaf area, define the leaf area. So in the model, we have this partitioning of the carbon to leaf, and using how much area I can produce by gram of carbon, we define leaf area by plant. The models that use temperature-based methods, we have the temperature-defined leafing expansion. So in the same way that you calculate this developed stages, we can calculate how thermal time units the crop expand to emit one leaf, and based on this, we can define how much leaf the crop have, the size of each leaf, and total leaf area by plant. And in this case, we don't have the carbon being a limiting factor. We don't calculate how much carbon go to the leaf. However, the most of models the combined methods, where I have temperature controlling the emission of leaves, and the carbon controlling the expansion of each leaf. So how the model works: in the first step, the model calculate how many leaves the crop expand based on the thermal time, and after this leaf you're gonna grow if there is carbon available for this leaf. Okay, this is one approach that you can use. So how can it be modeled mathematically? So in this example, we're gonna bring the combined methods where carbon and temperature are included in the system, and you can see that we increase the model hypothesis. So for more complex process, more detail you need to bring. So first, the temperature, we're going to define the emission of nodes in the plant. This is the phylochrome. The nodes will define the number of leaves in the plant, which have a size relate with the plant density. The leaf emission occurs until the complete growth of the main branch. From the end of the leaf emission to the beginning of the reproductive period, the leaf area increases due to the expansion associated with the carbon availability. So remember that when you talk about phenology, we saw that the models change the partitioning in function of the phenology. This is one example that until the beginning of the reproductive, the leaf area will increase in function of the carbon available to this crop. And the next, we have the leaf area decreasing after the beginning of the reproductive period and reach zero at the maturation. And crop stage controls the growth senescence of the leaf area. In this case, we saw that after starting the reproductive period, the crop will going to start the translocation of the biomass, and every day we have a senescence of leaf that will reduce until reach zero in the end of the cycle. And here is a abstract about how this model that you are studying works. We have these two different, one period it's increase in the leaf area and other period is decrease in the leaf area. And the driving variable in this case is the phenology. So you can see that from showing to emergence, there is no leaf development. From emergence to termination leaf growth in the main stem, we have all these factors affecting the leaf area growth. From this termination leaf growth on the main stem to the beginning of the seeding growth, we have the increase of the leaf area following the dry matter, and the leaf area development from leaf growth and specific leaf. So we have emission of leaf occurring in this crop phase, and here we have just the growth of the crop, the growth of the leaf in function of the carbon available to leaf. And from the beginning of the seeding growth to crop harvest maturity, there is no leaf development. But in the other side, we have this decrease in the leaf, that from emergence to the beginning of the seed grow, no leaf senescence, only grow associated with this condition. And from the beginning of the seeding grow until the crop harvest maturity, the Lithara Index will reduce linearly and reach zero at the maturity. So we are simulating the leaf growth more stable during the seeding growth, and after this period the crop will reduce to zero because of translocation. So this is a very simple way to simulate the leaf area index following these different crop stages across the cycle. So to make this model, the first thing that you need to define is here in function of our stage from emergence to termination leaf growth on the main stem. We're going to calculate how much nodes the main stem can have, following here the thermal, the temperature unit from showing. So for each emission of each node, I will require a thermal time accumulate divided by how much thermal time the crop will require to emit a new node. So here is the philochrome. Based on this equation, I can calculate how many nodes the crop are emitting every day in function of the thermal time accumulated in that specific day, and I'm gonna make this accumulation across time to get the maximum or the state variable of how many nodes I have in the crop that are gonna define the leaf number in the plant. After that, this is an experiment that was did where they evaluated the number of the main stem node in function here of the plant density and how much leaf area each plant have in this condition, in this different condition. So they adjust this equation where the plant leaf area, its function of this placon, that is a coefficient that define how much is the initial leaf area in the first node. So they observe that in the first node the crop has 1 square centimeters of leaf area multiplied by the main stem node number, elevating this other factor that they adjust here in function of the plant density for each one of these line in function of the plant population here. So here we can calculate in function of the plant density based on this parameter, based on the number of nodes in the main stem, calculate for the previous by the previous equation in function of the thermal time, and here I will define how is the plant leaf area in function of this factor. After that, I have a dial increase of the leaf area index that is defined by plant leaf area calculate for today less plant leaf area that I have in the previous day, multiply by plant density, and divide for 10,000 to get this conversion of needs from square centimeter to square meter. And I will define how is the the leaf area increase by day in the system. And here is the diagram representing this simulation where I have the thermal time by day, define the number of new nodes in the main stem in function of the phyllochron. This will define the maximum, the actual number of node in the main stem that will define the plant leaf area by each day. And based on this equation, I can calculate, including here plant density, I can calculate how is the gain or the increase of the leaf area by each day for this period from emergence to termination leaf growth on main stem. So in this preview crop stage or crop phase, I have this calculation every day in function of the thermal time, how the leaf area is increased. But when I change the crop phase from using here from termination leaf growth on main stem to beginning of the seeding of growth, the increase of the leaf area index will not gonna be in function of the thermal time, but in function of the leaf dry matter increase using here this unit and the specific leaf area for this crop that we're gonna define the leaf expansion. So until the beginning of the reproductive period, the seed growth, the thermal time define how many leaves I have, and I don't have more increase in this number when the beginning seed growth start. But if I have more carbon available in the system, these leaves that were defined previous will increase in expansion and in function of the leaf, specific leaf area and the dry matter available for this leaf area, you're gonna have an increase by every day. And this is the flow diagram for this crop stage that the leaf dry matter increase based in specific leaf area. You define how is the gain of leaf area index by day in this phase. And after the beginning of the seeding growth, we have this change in the flow where instead of increase leaf area, we're going to start the decrease of the leaf area. We're going to start the leaf area reduction by every day because we can simulate this senescence and the translocation of biomass from leaf to grain. So to make this calculation, you want to use this unit for thermal time in the beginning of the seeding growth, based in this difference between the thermal time, the maximum, the accumulated thermal time required for maturation, crop maturation, less the thermal time accumulated until the beginning of the seeding growth. I will define for each day that you define the time between beginning of the seed growth into maturation. Based on how many days I have for this period, I will define how is the daily reduction to when I reach the maturation, this value of leaf area index will be 0. So here we have this the leaf area index in the beginning of the seeding growth that you define how much is going to be the reduction of the leaf area index by day. So based on this accumulate thermal time from beginning of the seeding growth until maturation and how each is the leaf area index in the beginning of the seeding growth, I can define how many will be the reduction of the leaf area by day from the beginning of the seeding growth until the maturation. Okay, so you're gonna have this increase until of the beginning of the seeding growth, and after this period the crop start reduction into zero. So this equation is showing that from this maximum point until maturation, I have a rate of reduction linearly to reach zero in the end of the cycle. And our state variable, Lithara Index, will be defined by the Lithara Index of the previous day plus the increase of the Lithara Index by day that you calculate previous, and we have this reduction of the Lithara Index occurring based on the phase that you're gonna have. So until the beginning of the seeding growth, we have this increase occurring and the senescence is zero, but after this beginning of seed growth, the increase will be on a zero, and you have this decrease to update the value of the Lithara Index by each day in the system. Okay. So, and after we define the phenology, the leaf area by plant, we have this biomass production. Each house also have different way to be calculated. So the biomass production is basically in function of the photosynthetic rate. It depends on the leaf area and the interception of solar radiation and the other factors that can be included in the model. And here we have different approach that can be used to calculate the biomass production. We have the net photosynthesis that is used in the site, where the gross photosynthesis is calculated based on the available of energy and the light interception. This light interception is going to be a function of the Lithara Index, which loses through the respiration as a function of the temperature, in addition to expense for converting the material produced. So in this case, the model simulates a carbohydrate production, and after, based on the composition of the plant, we have this energy cost to convert the carbohydrate to another components in the system. And here we have an example. To produce 1 gram of lipid, we required 1.17 grams of glucose, that is the basic component for the carbohydrate. However, to produce the same 1 gram of cellulose in the crop, I need 0.11 grams of glucose. So you can see that the cost to produce lipid in the crop is like 11 times more than produces cellulose. So this are going to affect how the biomass is converted and produced based on the plant composition in the system. Another approach, very simple, is the radiation using efficiency, and where the dry matter produced is defined by the interceptor energy. Using this conversion, grams of biomass by megajoule that it's intercepted by the crop. And another approach also uses the water use efficiency, where the dry matter is produced by water transpired by the crop. So we have gram by millimeters of water lost by transpiration. So we have these different, some models have the two approach. For example, in the APSI, the model uses radiation use efficient for potential condition and water use efficient for attainable condition. In our example here, we're going to focus on the radiation use efficient, and here we have the hypothesis of the model, where the photosynthetic solar radiation intercept is linked to the Lithara Index. So remember that we have this Lithara Index as a state variable to define how our system is, and also as a driving variable for radiation interception. We have the radiation use efficient is adjusted by temperature. So if you have the optimal temperature, we have the maximum radiation use efficient. There is a relationship between intercept radiation photosynthetic activity and the dry matter production. And in this case, root dry matter is not included as a biomass produced, because when you calibrate the radiation use efficient parameter, we just measure above ground biomass. So this is one of our hypotheses. If I want to remove this hypothesis, I need to measure also the biomass produced, but above and below ground, to compute the total biomass produced by gram of solar radiation intercept. And here is our equation where the daily amount of dry matter produced gonna be function of the photosynthetically active radiation incident to the crop, multiplied by the radiation intercept by the leaf, multiplied by the radiation use efficient coefficient that define how much gram is produced by solar radiation intercept by the crop. To understand this equation, the first step is to understand how the fraction of photosynthetically active radiation intercept is calculated. We use this function. It's very applicable for a crop where the fraction of solar radiation intercept by the crop is defined by the Lithara Index, following this equation here, where we have this Lithara Index that you can simulate in the model, and this parameter that define how is the shape of this curve in function of the crop, in function of the type of leaf, in function of how is the angle of this crop, how the position of the leaf, if the leaf is more up or more linear in the environment. So this needs to be calibrated using experimental data or reference for each crop. So based on this equation, we define how much percentage of the available radiation is intercepted by the leaf in function of the crop that define these parameters, and in function of the Lithara Index in the system. The next step is to define how is the radiation use efficiency. Most of the models work with a potential condition for this radiation use efficient. So they define the maximum under optimal condition, optimum water, optimum temperature, optimal environmental condition for this crop. And after, we start to penalize this maximum value by different factor. And here we have example where this maximum value is penalized by mean daily temperature, showing that this relative radiation use efficient, represented by this TC rule, how you can adjust this value in function of the air temperature. So if I have 20 degrees Celsius, the radiation use efficient will gonna be the same than the maximum value, but if I have these intermediate values, we have this effect on the radiation use efficiency by temperature, because the crop is losing her efficiency to make the photosynthesis. We can include other factors. Here's an example how the CO2 can affect the radiation use efficient. Remember that when we define the hypothesis of our model, we don't include this, but I bring to show how we can model this. So if I want to include the factor of the CO2, I can use something similar to this, where I have the maximum radiation use efficient multiplied by temperature adjustment multiplied by CO2 factor. For example, here from our baseline, if I increase the CO2, I can have increase in this radiation use efficient by the crop. Okay, so for this I need to check if my crop has a response to CO2 or how is the shape of response in function of the carbon dioxide concentration for each crop. I also include the water stress factor that you're going to adjust the radiation use efficient. Here we have an example that you can use the how much water available in the soil has to the crop in relation to the transpirational demand for this crop, and define if I have no water depth, the radiation use efficient will be 1 and the maximum value. But if I have water depth reduced here, I have a penalization in the radiation use efficient by water depth. Okay, so we can put this factor together to make a simulation of attainable yield, for example. So if I want to simulate a potential yield, I include the maximum and the temperature response. But if I want to include climate change scenarios, I can put CO2. If I want to simulate attainable yield, I also can include the water stress factor to penalize the radiation use efficiency. And here we have the diagram showing how the dry biomass is going to be produced. I start here with Lithara Index, and this factor defines how much radiation is intercepted by the crop based on the photosynthetic radiation. And in this the daily production, I'm going to have the total production of the biomass by the crop accumulated across the time. And to get this daily production, I need the temperature that will affect the temperature function response to radiation use efficient, following the 4 values for temperature. This temperature will adjust the radiation use efficient based on the maximum value to produce the biomass. So this is the diagram showing how the biomass can be simulated. And the last topic after the biomass is produced, this is partitioning for different parts of the crop. Remember that leaf area by plant has one step after beginning, after finishing the emission of leaf, that the leaf growth will depend on how much biomass will partitioning to leaf. So for this, we can use different levels. We can use a simple approach where the biomass is partitioning using the harvest index or linear harvest index, where this approach, the harvest index, is going to be used to, in the end of the cycle, I will get the total biomass, and one part will be defined as grains in the end of the cycle. For example, I have a total of biomass produced. I know that 50% of the total biomass for soybean is grain. I just get the grains and estimate the yield based on this total biomass. Another approach is use a linear harvest index, where it simulates a linear growth of the grain dry matter during the grain filling period. So when I start the growth of the grain, every day I'm going to have a part of the biomass being partitioned into grain, including this translocation from leaf and other crop parts to grain. And you have a more detailed approach that use the limited surge, limited sink, or combine. The limited surge, the grain growth will gonna be limited by carbon supply with no grow limitation. So if there is carbon available, the grain will continue increase. However, in the limited sink, the grain has a maximum amount of the carbon that can be observed, and even if there is carbon available, the growth is limited. So every day is produced biomass to grain, and this grain have the maximum amount of the carbon that the grain can get. So for example, if I have a problem and in the flowering period and I have less flowering than the potential, if I use this limited sink, the yield can be limited by the number of grain in the plant that is getting carbon. Or use the combine approach where the balance between surge and drain sink are used. So for this example, the biomass partitioning, we're gonna use three sink in the system. We have the leaf, stem, and the grain. The phenology is a driving variable to partitioning. Root is not included, and the grain grows with new dry matter and with translocation. So here we have the definition. Each active sinks, we're gonna receive the carbon that is produced by every day in function of the phenology across the crop cycle. Here is the definition, how the model simulated this process. So during showing to emergence, there is no dry matter production and distribute. So we're gonna be 0. From emergence to beginning of the seed grow, I have this partitioning coefficient to leaf is obtained. Dry matter distribution to leaf is calculated as production of the leaf partitioning coefficient and the daily matter production. And my dry matter is partitioning to stem. So for this period, I calculated how much dry matter go to leaf and the other part go to stem. However, from the beginning of the seed grow until the end of the seed grow, all current dry matter production is partitioning to seed. We have this part that is mobilized to grain, and seed grow rate is adjusted by biochemical difference between seed and vegetative organs, where after this, the finish of the grain growth until the harvest, there is no dry matter production. So this is very important, this conversion, because remember that to produce lipid or protein, the energy cost is too high than other parts of the crop, and I need to convert this to get the real value for the crop. So here in the vegetative org, the leaf and stem. So I have this GLF, that is the dry matter to leaf. That is function of the maximum, the dry matter produced by day, and FLF is a fraction of these biomasses that is put in the leaf. And for stem, I just have the difference between what was producing that day less what was put in the leaf. And here is an example how the total dry matter in the crop is related with the leaf dry matter. And the authors use this function to define this factor for the crop. So until this point, I have almost linear condition, and after I have less leaf to less dry mass to leaf. And this is calculating following these equations. After the vegetative period in the reproductive organ, I have the grain filling, where the dry matter available to be translocated is defined by the total biomass that I have in the beginning of the grain filling by the fraction that is translocated. And this translocation will be defined between the end of the translocation rate to the grain is defined by the thermal time between these two phases and the dry matter available. So in the beginning of the terminal seed growth until the beginning of seed growth, I have this time to translocate all biomass that I have available in the system to the grain. And the next step is the daily grain growth, is defined by how much biomass is produced by day, by the actual condition, plus the translocation defined here from how much biomass I have in the other parts by the fraction that can be translocated. I have these two, multiplied by the cost to conversion, for example, the leaf area material to grain, and how is the cost from the base component to the composition of the chemical in the grain, for example. And in the end, I have this, the actual value for grain weight is the previous day plus the new biomass that is put in the grain. And here is the final diagram how the dry matter distribution occur in the model. So we have different factors and different conditions where the daily dry biomass produced by day is distributed to the different components. I have here. So here we have the biomass, the fraction of the biomass that is put in the leaf. So we have this biomass in the leaf. Then you want to have the final value for biomass that will affect the how much dry biomass by day is put in stem to define the leaf and stem biomass, and following this factor that define the factor between biomass to leaf and stem. After we have the daily growth of the seed, a function of these factors, include here the total biomass that I have in the beginning of the seed grow that is translocate to the grain, and this conversion rate to get the final biomass in the grain across this condition. So in this approach, we are using the sink and the surge to define how much is produced, how much each component can get, and how is this interaction. So to finish, we have these all components that are being simulated for potential yield, and all these are affecting each other. For example, we have this daily biomass produced is in function of the Lithara Index, and the distribution of the biomass is function of the phenology. So we have many interaction occurring in the system. Okay.